As we go on to the second part of Chapter 5, Section 3 on linear programming, we're going to do some stuff on page 268 where it says explore and discuss, and then we're going to go on a little bit further. Now, in our first video on this section, we showed you how you might end up with this. This would be one line, this would be the other line. They intersect there, but it's both less than or equal to. So we were shading under, and it gave us something like this. Now we were also asked to do the corner points. Now, corner points are where they hit an axis or intersect. And in a sense, there's also 0, 0, we said, was a corner point. Now, what they also give us is some sort of price equation, where they're saying the price of something is 2x and 3y, and we kind of keep that in reserve. And then they ask us to make a corner point table. Now you might say, what is the significance of this? And I see they're cutting the grass out there. I guess that's a Monday morning thing. Well, we start to list our corner points. 0, 8. 6, 9, 10, 0, and of course if we listed 0, 0, that would all just be 0. So we'll leave that one out for now. Now, what do we do next? Well, we use this as a guide. It's 2x plus 3y. So we will substitute our x, y values into this equation, and when we put a 0 for x, 2 times 0 is 0, 3 times 8 is 24, so our value is 24. Here we're going to put a 6 and a 9, 2 times 6 is 12, 3 times 9 is 27, that gives us a corner value of 39. And the same thing here. We put a 10 for the x, we get a 20. This is a 0. Our end result is 20. Now, one of the questions you'll get in the quiz bees and in the practice will be, what is your total corner point table value for these coordinates? Well, that's how you get them. And then they sometimes ask, well, what was the x here? Well, the x here was 0, and the y is 24. Here it's 12 and 27, 20 and 0. So this is sort of intuitive, and that's what a corner table is like. But let's go on to some of the theorems that are listed on page 269, the next page. Theorem 1. Optimal values. Optimal values are sort of the best, taking into account various situations. So, generally speaking, your optimal values are at the corner points. They can be one or sometimes more. So as we look at this example, and we look at our corner points, remember this is the feasible region. what is our optimal value? Yes, it's 6,9. How do we know that for sure? Because when we put it into our corner point table, this is the highest. That's our optimal value. Now, another thing from the past, and I think I mentioned this very lightly, is this graph bounded or unbounded? Well, as you see, it's all within bounds, so this one is bounded. Now, when you have, as they're saying, your feasible region is bounded, then there are a minimum and maximum values. That is, minimum and maximum values exist. Now, the minimum value would probably be your 0, 0, and your maximum value now we know is 6, 9. And I'm going to put another diagram up and we'll get to our other 2 points here. Now, I didn't make these very fancy, they're just to illustrate something. As we look at this particular graph, we see the feasible region is there and in a sense extends beyond. So in this particular graph, the feasible region is unbounded. And as the theorems states, then a minimum value exists. So a minimum value exists, but a maximum value does not exist. Because since this extends on into infinity, you cannot define a maximum value. But you could get your minimum value. That would be this point right there, a corner point. And then in example C of our theorem, if a feasible region does not exist, here there's this area, here there's this area, there's no interaction between them. So here there is no true feasible region. Then there is no minimum or maximum values. So again, in summary, after we do our graphing, and we've had lots of practice in that, we look at our corner points, and I'm going to go over some examples as we continue our lesson on this. I had a section where the fellow was mowing the lawn, so it's kind of noisy, so I'll just do this one again. So in Theorem 2, they talk about if the feasible region is unbounded. So this is an example of unbounded. Why is it unbounded? Well, because this is up toward infinity there. That would be unbounded. But it does have a minimum value right there where the lines intersect, but it does not have a maximum value. Now in example C, under our theorem, it says if there are no feasible regions, that is, there was this area, but nothing where they actually overlapped. There would have to be some overlapping. So in a sense, this shouldn't really be shaded. But indicate that's up there, this is down there. There's no overlap that would cause a feasible region to be founded. There's one other little example they give you in the book where the feasible region looks a little bit like that. This is the part that's dark, and these would be the corner points. Now, a little note that when you are doing your corner point table, if you check out some of these, and all of these are minimum values, there would be more than one minimum value. And sometimes when you follow a line like so, points along this line may be maximum values. The only way to find that out is if you do a corner point table and then look at your values. And again, that's all related to what they give you as a pricing formula, or some formula that looks like this. This is how they relate. Okay, we'll go on to an example now. All right, we're going on to physically now do example 2 on page 270. Now what they're asking us is a minimum and maximum based on this, z equals 3x plus y, subject to these three equations or inequalities and these qualifiers. So this is what puts it into our, later when we graph it, our first quadrant. Now as we do these, and I brought a ruler, what would be the strategy of starting to do it? And again, you're going to need graph paper. I did it without graph paper, and you'll see I'm a little bit off, but with graph paper you get some very good results. So here's an inequality in standard form. And we said when it's in standard form, a good way to start to graph it is to find your x and y intercepts. And for that then we use an x and y intercept t-chart. That if x is 0, y is going to be 20. So we put the 20 there. If y is 0, we put the 0 there, and then just divide both sides by 2, and that gives us x is 10. And then I did that for all of these. And then what I did, and I color-coded them, so this would be a black line, this is a blue line, and this is a red line. So perhaps without stopping, let's see if I can just zoom it in. So then for our black line, I use these coordinates, 0, 20. So 0, 20 is right there. And then 10, 0. 10, 0 is right there. And I drew the black line. And notice this one is less than. So in a sense, I'm shading under the black line. In my blue line inequality, I have 0, 36. So one spot above 35. And again, my graph is a sketch. And when I divided if y was 0, divided both sides by 10, I got 3.6. So that was about there. And then when I did inequality 3 in red, I had 0 and a 7.2, so 7.2 is right about there, and that went down to 18. So there are my 3 lines. And by the way, your textbook has a very good picture of this too, but this is not too bad. So on the blue line and the red line, they said shade above. So our feasible region is what I have colored in green. And then what are my corner points? Now again, if you did this on graph paper, you ought to be able to pick out the corner points pretty easily. Since I'm just sketching, my sketches are off. Some of them are close. So this upper corner point here is 2, 16. I'm off a little bit. This one is 3, 6. So I'm off there, but again, that's the actual point. And this one is 8, 4. Now, what I have here is something that we did in chapter 4, and we're picking it up. How can you find the corner points? Remember, these are intersections of these inequalities. So what I did is I converted equation 1, or inequality 1, into its matrix form, and equation 2 into its matrix form, because just by multiplying each of these by a -1, my y's cancel out. I add this up and I get a -8x equals a -16. Divide both sides by a -8, I get x equals 2. And then if I use one of these and put the 2 in there for x, I get y is 16. So I know that's a good point, even though my graph is not done that accurately. Okay, when I get to equations 2 and 3, remember this is the blue and the red line. Blue and the red line. Put those into that little form. And I had to fiddle with the second equation. I multiply each term by -5, so my x's would cancel out. And eventually I get it. So this is a method that you can use to find your corner points. But now what we need to do is to make a corner point chart. Okay, what I've done is I've taken each of our points, our coordinate pairs of points, and put them into a corner point table. It's a little bit different. I have a different order than the textbook, but it's similar. And again, this is what our minimum and maximum is associated to. So I just set it up. X is 2, so 3 times 2 plus 16 gives me a 22. Our x value here is 3, so 3 times 3 plus 6 is 15. And 3 times 8 is 24, plus 4 is 28. Now an interesting thing happens. As you look at this particular graph, we're saying, well, what is our maximum? Well, according to this, our maximum is the largest number, which is 28. The coordinate pairs of that is 8 and 4. So this happens to be our maximum. Well, what is our minimum? Well, as we look, we see we have a 15 at 3, 6. 3, 6 is right over here. That's our minimum. And again, it might not look like a minimum. So the only way we were able to find that out was to take these ordered pairs, apply it to this equation, and then do our corner point chart, where you might think that this point would be the optimum or maximum, but that's actually in the middle. So again, something interesting. We'll do the other part of this problem. I'm not going to do it in this great a detail, but we'll work on it nonetheless. As we go on to part 2 of example 2, we've changed our minimum and maximum value subject to these. And what we would do again would be to make an X and Y t-chart. Get our values and then plot our lines. And since this one is greater than, our lines would be, our shading would be above. And then we also have a qualifier up here, y is less than or equal to 20. Well, that's this line. And it's shaded below, so in a sense it's bounded up here, but unbounded in this direction. So if in case B over here, the feasible region is unbounded, then a minimum value exists, but there is no maximum value. Again, why? Because it's unbounded this way. Now, they then ask, well, what would be the minimum values? And we said minimum and maximum values are always at corner points. So we've listed all the corner points and then applied our little formula up here. And I have all the work, and again, this is in your textbook too. So we see this is large, large, small, and wait a minute, this one is the same value. So let's think about that for a moment. When they're the same value, well, what does that mean? Well, actually what it means is any point from here to there along this line, all these ordered pairs would be minimum values. So in this case, and they're introducing a new word here, multiple optimal solutions. Now remember, optimal is the best, doesn't necessarily mean maximum. In this case, it's referring to minimum. And since there's not just one minimum value that's low, all along this line are optimal minimum values. So that's why we have this word introduced, multiple optimal solutions. In example 3, on page 271, it starts off giving some of the parameters. It's a long paragraph with lots of information. It says a hospital patient is required to have at least 84 units of drug A and at least 120 units of drug B. Now, there is a drug D that has some qualities, but we want to minimize that, and I'll get into that a little later. So after reading everything, they have taken the data and put it into this chart. There are two types of meds here, substance M and substance N, M and N. And in the paragraph, they give you all of this. So again, making a chart is probably going to be useful for you. Then you're going to take this chart, following this qualifier in a sense, that C equals 3x plus y. They give you that. and then you set up your inequalities. So there's 10x plus 2y equals 84, or is greater than or equal. This is the minimum you must have. So greater than or equal. And then the same thing for drug B. 8x plus 4y is greater than or equal to 120. That's where these inequalities come from. And then we have our other qualifiers that it's in the first quadrant. So what I did is I took each of these inequalities, put them in my special t-chart to find my x and y intercepts. So then the black line is 0.42, 8.40, and then the other line, the red line, is 0.30, 0.30, 15, 0. I drew my lines very carefully. They intersect at this point. That's pretty close for a graph sketch at 4.22. So that's where we are right now. I wanted you to see how we got there. And of course, all of this is in the textbook as well. Okay, as we go on to interpret the results that we have, we've done a corner point study. We've done these corner points before. So we've taken our corner points. Remember, 0.30 is not a corner point of the feasible region. The corner points are this, this, and this. So when we put that into our little constraint formula, we end up with 42, 34, and 45. So we're looking, since this is an unbounded feasible area, feasible region, there's no maximum, but we're assuming that if you get more of the drug than needed, that's going to have a harmful effect. So here we have our optimal point, our minimum amount of drug to use, and that would be 34 units. Now this ties in with this too, because we want to minimize this. By using this amount of drug, that is 4 units of the drug A, 22 of the drug B, it minimizes this. Because anytime we use more of these, as we move out into it, it has, in a sense, a harmful effect. So this is minimized at this particular point. 4 of A, which is your x coordinate, and 22 of B, which is your y coordinate. Now I did a lot of these at home over the weekend just to practice, to see how it works out. These are challenging. And again, if you wanted to find this mathematically, you would just solve these equations by matrix or any means that you know, and that will give you this minimum here as well. Well, again, you're going to have your practice, your quiz bees, and eventually your test on Chapter 3. And hopefully these have been helpful.